All right, so I had a little bit of trouble with my electricity yesterday, so we'll finish up this chapter 3 problem set right now. And so number 5 asks us to do a few things. We have to do the following 4. We want to calculate we want to calculate the following. We're going to find the intervals where the function is increasing and decreasing, where it has local maxima and minima. We want to identify the intervals where the function is concave up and down, and finally see if there's any inflection points. So this is a very strange function. I looked it up on Symbolab, and it really is a very hard function to describe. It looks like a very sharp parabola, but you can see at the very least we do have a single minimum, a relative minimum, which is also a global minimum. And then we have 2 points where the function crosses the horizontal axis. But because the numbers are so large, it's really hard to see what's happening with this graph. So anyway, let's do this. We'll start with the first derivative. So in other words, we'll start by finding the critical points. One of the good things about polynomials is that you're not going to find any discontinuities or any sharp points. They're going to be smooth and continuous throughout. So everywhere where the first derivative equals 0, we're going to have a critical point. So let's figure this one out. Now, using the power rule, we'll have 4x cubed minus 18x squared. So we'll set that equal to 0. Okay. Set these equal to each other, which means that x cubed could be also written as 18 over 4x squared. And now let's just simplify this a little. And what does that leave us with? I'll tell you what, let's do this so that we can factor. Now, why are we doing this? Because then you can see that if this product equals 0, it must be true that if x squared equals 0, this product will equal 0. And if x minus 9/2 equals 0, the entire product will equal 0. So that implies that 0 and 9/2 are the critical points. All right, so yeah, this is the kind of case where you could have, like from here, if we just divided both sides by x squared, you would have been left with x equals 9/2, but you then would have overlooked the fact that 0 also solves this equation. So sometimes it's easier to break it up and factor it rather than solve it directly. So we do have the 2 critical points. And so what we're going to do is test them to see if they are maxima or minima. Okay, so for x equals 0, so we'll imagine that there's some point in our curve where x equals 0. It's hard to say from that graph that we were just looking at. I'll tell you what, let's just algebraically solve for the first derivative on either side. Or actually, rather than that, why don't we use the second derivative test? Let's check the second derivative at each of these 2 points. So in order to do that, although we can certainly use the first derivative test, it might be quicker to use the second derivative test. So we'll take this 4x cubed minus 18x squared. Okay. And then we'll take the derivative of the first derivative, which is what we mean by the second derivative. So again, remember f of x was originally 4x to the 4th minus 6x cubed. Then we would have f prime of x is 4x cubed minus 18x squared. And then that means that the second derivative, which is the derivative of the first derivative, meaning that we're applying the same rules to it, becomes 12x squared minus 36x. Okay, great. So f double prime of 0 Okay, now remember from the slides, this means that at this point, the second derivative test is inconclusive. All right, so now what we could do is then turn around and try the first derivative test, since the second derivative test failed. I mean, it was a great idea, but it was inconclusive. That's one thing that can't happen with the first derivative test. It always gives us a result. So let's try this. Since the point is 0, let's try a point to the left of 0. All right, so we're going to have now when -1 cubed is -1 times 4 becomes -4. -1 squared is 1, so we're subtracting 18 times 1, which is 18. So we ultimately end up with -22, which is of course negative. So then let's also try 2. We need a value on the right, or 1. 1 is fine. Let's do f prime of 1. It might be a little quicker. Okay, so now this means that this point is neither a maximum nor a minimum. Okay, so we don't have a name for it. It's one of those cases where you might see something like this. Where at that point, slope is 0, but it's clearly not a minimum or a maximum. Say the function keeps going like this. We had a few graphs like this in the slides. So that means this one the critical point 0, critical value 0, is neither a maximum nor a minimum. All right, so let's hope we have better luck with x equals 3, 9 halves rather. It was 9 halves. We'll try the second derivative at 9 halves. So again, the second derivative is 12x squared minus 36x. All right, so let's evaluate that at 9 halves. Okay, so 9 times 36 is 324. Okay. So we have 972 over 4. Now, if I want to convert this into fourths, I'll be doubling the numerator and the denominator. So it's pretty clear that this is a positive number. Specifically, it's 324 over 4. So incorrectly wrote here is 2. And that's positive, whatever it is. So what that means is whatever is going on at 3 not 3. Why do I keep saying 3? It's 9/2. Okay, 9/2. So that 9/2, and we can calculate the y coordinate from the original function. Let's just do that real fast. X to the 4th minus 6x cubed. So f of 9/2 equals so 9 to the 4th is 65/61. 2 to the 4th is 16. Yeah, here we're going to have if I multiply this by 6, 43/74 over 8. Okay. Now, of course, we need a common denominator. So let's take care of that right now. So I'll double the numerator and the denominator. So that leaves me with 87/48 over 16. So let's see what we have. Minus 21/87 over 16. It doesn't look like that can be reduced any further. So we'll write this as negative 21/87 over 16. So that is our minimum point. And since it's the only minimum point over this entire domain, it is also a global minimum. All right, but they didn't ask for that. They only wanted the relative minima and maxima. It just so happens that there's only the one minimum, so therefore it must be both the local or relative and the global or absolute minimum. Okay, so that part is done. What else do they want to know? Yeah, so intervals, well, clearly, because this is the only minimum, the intervals where the function is increasing and decreasing, it's only, well, actually, since we did have critical points, remember, one of them turned out not to be a minimum or a maximum, so we should probably check it out. Let's see. So actually, we've already done this for 0, haven't we? When we were looking at 0, no, actually, we didn't. Not yet. We were using the second derivative test there. Oh no, here it is. Here it is. That's right. So in the area surrounding 0, the curve was decreasing. The slope is decreasing at both points. So let's see. So even though this was technically a critical point, it's not a minimum or maximum. So the slope is negative on both sides of this point. So the function is continuously decreasing until we reach this critical point, which happens to be a minimum. So if we test the first derivative on either side of this point, we would expect to see it go from negative to 0 to positive. Okay, so let's just quickly confirm that. So we have f of prime of x equals, once again, I guess I didn't memorize it, 4x cubed minus 18x squared. So let's try f prime of 4. That's slightly to the left of this function. All right, so what's that gonna be? $256 minus 288. Okay, so it's negative as we expected. And then we'll try 5, which is a point just to the right of this critical point. All right, what do we have? 500 minus 450. Okay, so just as we expected, the sign of the first derivative went from negative to 0 to positive. And that implies that this point is, well, we know that it's a relative minimum, but it also implies that the function f of x decreases from negative infinity up to 9/2 and increases from 9/2 up to positive. Okay, great. Now, by the way, we're going to have, when we look at the idea of convexity or concavity or concave up or down, because there's only this one critical point, there's only going to be, well, we'll see. You won't have several changes in concavity. In other words, we do not expect to find an inflection point here. So, but let's try that. Let's see what it is. Okay, or let's first set the second derivative equal to 0. So the second derivative, once again, is here. Sometimes it lets me copy it, sometimes it doesn't. 12x squared minus 36x. Set that equal to 0. Okay. So we have 2 points where the second derivative is 0. And they want to know where the function is concave up and down. Now, keep in mind, an inflection point means that the concavity changes at that point. Now, earlier we saw that the second derivative of the test is inconclusive when x equals 0. So if we test the function, let's say to the left of x equals 0, all right, so we have a positive second derivative just to the right of it. Negative. And then again, with the 3, we can use this as the point to the left of it. F double prime of 4 is going to be 12(3) squared minus 36(3). And that's going to give us 108 minus, let's see. Ooh, 10, is that right? No, what I, that would help if I substituted the right number. Here we go. All right, let's try that again. 192 minus 144, so it's positive. All right, so let's see. So let's break this out as intervals. Second derivative is positive, negative, and then positive. Okay, so that means it's concave up here, concave down, and then concave up. Okay. And again, the graph itself, it's very hard to tell by looking at it. To confirm this, I don't know about you, but I'm finding it very difficult to read anything out of this graph. But that's what the calculus results are telling us. Okay, so that should do it. All right, well, that problem was pretty tough. But usually we don't have to go through quite so many steps. We had to do a little bit of everything with this problem. So it was good practice. We finally got it done. The others won't be quite as difficult. The rest of these are limits, where we may need L'Hopital's rule. Not necessarily. We don't always need L'Hopital's rule. All right, let's try this one. Now, first of all, you notice that in each of these cases, it looks like they're all, except for one. Well, actually, no, not all of them. Some of these are asking us to evaluate the limit as x goes to infinity. So you can see, if I plug in infinity here, oh no. So that means that we can go ahead and use L'Hopital's rule. So let's do that. So basically what it's telling us is that if we end up with infinity over infinity, all we have to do is take the derivatives of the numerator and the denominator and try again and see if you get a result. So here you can see this is working out well because the derivative of 2x minus 5 is just 2, and this derivative is just 4. So it's just a half. You can see why L'Hopital's rule is really a very hopeful result because it can save us a lot of grief with some of these horribly complicated limits. All right, now how about this one? Well, you can see just by looking at it. This is, by the way, this is negative infinity. You have to look very carefully at it. It's negative infinity. So you're going to end up with this is negative as well. It's going to be now, by the way, this also we didn't specifically mention this in the slides, but negative infinity over negative infinity, we can also use L'Hopital's rule. Okay. I mean, when you think about it, the negatives do cancel each other out anyway, but just so you know that you can use L'Hopital's rule when it's negative infinity over negative infinity, as well as positive infinity over positive infinity. Now, again, we have two polynomials here, so we'll use the product rule to solve for their derivatives. First, here we'll have 9x squared minus 2. And actually, you know what I should have done? I forgot to write. So we'll have 9x squared minus 2 over 2x plus 2. All right, what happens now? All right, so when you plug in, so we still have negative infinities all over the place. So wait a minute, is there something else we can do? Maybe we could factor this. Let's see. Oh, okay. Well, this is okay. So you know what we can do here? There's another rule which we briefly mentioned once before. And you can see it didn't work out with the L'Hopital's rule. So another option we have is to do this. Go through the entire ratio, find the highest order of x, and divide all the terms by that. Okay, in other words, here's what we're going to do. Since x cubed is the highest power of x, let's do this. And you might say, well, how does this help us? Well, we got our fingers crossed that this will enable us to solve for it directly. So now make sure it's the highest exponent. So I'm going to be left with, in the numerator, 3 minus 2 over x divided by 1 over x plus 2 over x squared plus 8 over x cubed. So, let's see. No, that didn't work either, did it? So it turns out then we can try again with x squared. Usually you go for the highest, but if that doesn't work, you see what the problem is here. I'm going to end up with a bunch of zeros in the denominator. So here we divide through by x cubed. That didn't help. It made it, we still have a mess in our hands. So try this time. Divide through by x squared. Now, there's no guarantee that that's going to work either, but certainly we know that x cubed didn't help. We also know that L'Hopital didn't help. And sometimes, I mean, I don't see any obvious way of rearranging that limit algebraically. Let's go. The document is not cooperating. Hold on. See, one of the problems with this writing, it's wonderful as far as it goes, but it really does suck up a lot of memory. And so sometimes the document gets a little funny. Especially when I'm online. I'm frantically trying to save it now so I don't lose my work because it could blow up any minute now. I can't tell this one. I need no. Oh my God. I'm gonna be pretty annoyed if I lost my mark. No, here it is. Okay, it was just tired. Okay. This is why you've got to save your work like every 3 seconds. It's just unbelievable. All right, I think we're safe now. All right, anyway, let's grab this again and try x squared. You know, it's like one thing or the other. It's the either the internet's got to act up or the Zoom has to act up, which it does sometimes. Sometimes it just stops right in the middle, or else the Word has to act up, or possibly my tablet has to act up because this semester my tablet has broken down on me. It's got to be one of them. Let's see. You know what I'm going to do? I'm going to turn this thing off. Again. All right. Maybe it's had its meltdown. So anyway, I'm going to try dividing through by x squared. And while we're at it, I'm going to save it one more time. I really don't trust it. Okay. So then we would get 3x cubed minus 2x over x squared, all divided by x squared plus 2x plus 8 over x squared. Now, how does that help? We're going to have 3x minus 2 over 1 plus 2 over x. Okay, so it may not look like it, but we're in pretty good shape now. And here's why. Because direct substitution of negative infinity will result in so we actually end up with negative infinity over 1, which we can simply write as negative infinity. Okay, so yeah, the limit can be negative infinity. In fact, if we were to graph this thing on Symbolab, it might be easier to see why this is happening. But before, you know, when you have only infinities in the numerator and the denominator, that doesn't work. So let's plug this into Symbolab just out of curiosity. So we have 3x cubed minus 2x, all divided by x squared plus 2x plus 8. All right, let's see what this thing looks like. Yeah, Symbolab's thinking about it. That suggests that it's going to be a really crazy function. Either that or it just refuses to work. Why not? It's been one of those days. Yeah. See, this is why, I think I may have mentioned this at the beginning of the semester. If you're really serious about math, I mean, Lab is fine, but it's free and all, but if you want the real thing, you've got to find a professional package like Mathematica. Let me just quickly show it to you. Wolfram makes it, they've been doing this forever. This is powerful stuff. Now, here's the great thing about Mathematica. It is not free normally, but virtually every college in the country has cut a deal with them where you can get it for free as long as you are in school. So your school will have somewhere on its website, if you go to the IT department, they'll have information about what software they have. They all have Word and they all have all the Office products, but they probably have this one too. I know Certainly Purchase does. And so basically you get a license, an educational license, and then everyone who goes to school can share it. This is basically Symbolab raised to the 100th power. Okay. It's crazy powerful. The only problem is it takes time to learn how to use it. Okay. But if you're going to do this for real, I mean, you're going to major in math and continue to get into more advanced courses, it might be worth your while to get your hands on this and learn how to use it. Because this is a professional version. This is something that professional mathematicians use. You can see it has some pretty cool graphics capabilities, but anyway, that's like the gold standard for math software. All right, anyway, now I've had my say, because Symbolab is disappointing me today. So we're not going to get a chance to look at this graph and understand why this is happening, but we do know that the limit is negative infinity. Okay, so that one was kind of a headache to find. All right, well, God, what else do we have here? So here we go. Now, again, a direct substitution is going to leave us with infinity over infinity. So let's try L'Hopital's rule. So we're going to take the derivative of the numerator and the denominator and try again. So the numerator is a breeze. Now the denominator, we have to be a little careful with it because it does require the chain. So g of x is radical x squared plus 1. Let's rewrite this as x squared plus 1 to the 1/2 power. So what we can do is recall the chain rule. It can be written as dy dx equals dy du dx. So let's write this function as y equals u to the 1/2 power, where u is x squared plus 1. And that implies that dy du by the power rule. And over here, du dx is simply 2x. So when I plug that back in, dy du is this 1/2 u to the minus 1/2. Du dx is 2x. Now I simply replace x with its definition. All right. Now the two, by the way, if you notice the half and the two cancel each other out. So we can write it a little simpler as x over radical x squared plus 1 if we want. So then what we're taking the limit of is three over all of this. Or in other words, you can rewrite this as, okay, Now, did that help? Um, I don't know. If we directly substitute now, yeah, well, that's very unfortunate because we still have infinity over infinity. So I think what we're gonna have to do is do some division. All right, let's go back and grab the original. Oh, you know what I forgot to do? I forgot to plug in this x over radical x squared plus 1. Okay. Let's try the division approach. Okay, so this way we do not affect the value of our results. Okay, so that didn't work either. So let's try x squared. Okay. Yeah, that's gonna be tricky. Um, I know what the problem is. It's the square root that's holding it up. All right, let's get this out of here. All right, we're gonna have to rewrite this slightly. All right, so here's what we're gonna do. Instead of writing it the way we did before, I'm gonna write that as the square root of x squared because it's the same thing, right? And so that means what I've actually got here is this. See, now that's the tricky part. So dividing by x is the same thing as dividing by the square root of x squared. That way I can consolidate these two square roots. And so I actually end up with limit 3 over radical 1 plus 1 over x squared. See, the beauty of this is that now direct substitution gives me this. Okay, so the limit of just 1 over x squared by itself as x goes to infinity would be 0. So I actually end up with what an ordeal that was. Oh my God. Now, I guess what we could have done initially is, I guess we could have simplified this. What if we tried, let's just for the fun of it, let's just see something here. What if I chose to rewrite this? Hmm. Well, I'm not so sure that's helping. All right, never mind. It was just a thought. But anyway, so that nightmare is over. Man, we've had some really nightmarish problems here. Not to mention the lack of cooperation from the technology. Although at least the power didn't go out today. I must say that yesterday, and it wasn't long. It's just long enough to make a mess out of everything. But all right, anyway. So here we go. Let's try some of these. So direct substitution here, you can see is not going to work because we're going to end up with e to the infinity over infinity. All right, so let's try L'Hopital's. By the way, it's very hard not, when you first come across his name, it's the most natural thing in the world to try to spell it as hospital or something like that. So we'll try. So remember, the derivative of e to the x is just e to the x. The derivative of course, x is just 1. And that's actually 0. E to the infinity is 0. Okay, because you're raising it. Oops, sorry. No, it's not. What am I saying? I was thinking of negative infinity. So this is just infinity. Okay, that's good. Okay, so in other words, we initially had infinity over infinity, which is not an answer. Infinity is a perfectly acceptable answer for a limit. Okay. If that had been e to the minus infinity, by the way, the answer would have been 0. All right, now look at this one. Sometimes they kind of take care of themselves. I'm going to rewrite this. If you notice, x squared minus 9 can be factored as x plus 3 times x minus 3. The reason why we need to do this, we don't need to do this, do we? Because we could have just directly substituted and still got to the same point. Yeah, I'm not going to do this document all over again, that's for sure. So in other words, direct substitution gives you zero, but you know what? That would have worked with the original expression anyway, because there was no danger of division by zero. So while that was a very clever thing to see and do, it wasn't really necessary. I mean, it's fun to show off your cleverness, but sometimes it's overkill. All right, now what's going on here? So we have direct substitution would give us 0 over sine 1. So we go to your calculator. Um, it doesn't matter what it is. We don't need to know the exact value of sine 1 because 0 over that is just 0. Okay, it's like 0.84 something. 8. Oh, for God's sakes, let me just write it in here. And it's just, it doesn't even matter what that value is. As long as it's not 0, then we're going to end up with 0. Okay. Now, look at this disaster. Now you can see for yourselves. Well, first, let's see what happens when we plug in 0. It's probably going to be a mess. It has that look to it, doesn't it? Yes, hold on one second. So direct substitution would mean um, oh yeah, no, this is no good. Okay, but here's what we can do. You might recall the concept of conjugates. Whenever we have something like this, because only the sign is different. And you might have run across this idea too if you're looking at complex numbers. We refer to these as complex conjugates. Of each other. And we can often put them to use to simplify very messy expressions. So here's what we're going to do. I'm going to multiply this by 1, but it's a very complex form of 1. What I'm going to do is multiply the numerator and the denominator by the conjugate of this horribly complicated numerator, because I suspect that will make things easier for us. Now, the beauty of having conjugates like this is that when you multiply them together, you're going to end up with this. Okay, so that means, and you can prove this with FOIL if you want to. You're going to have radical 1 plus x squared minus radical 1 minus x squared. All now in the denominator, of course, we have a mess. That's okay. Because now when we substitute zeros throughout, we may just have ourselves an answer. Actually, I'll tell you, let's simplify just a little bit. So in the numerator, I have 1 plus x minus 1 minus x. Now, when I drop these parentheses, I'm distributing this negative across both of these terms. Do not overlook that. What is the numerator reduced to? Oh, it looks like we have 2x. Which is nice because that cancels out. Now we can finally substitute the zeros. So we end up with 2 over radical 1 minus radical 1. Oh, no, I think I did something wrong here. I knew it. The denominator is the sum. Okay, so this should have been plus. Yeah. Plus, plus, plus. Yep, that's what I get for not being more careful. Plus, plus. That's more like it. And so the final result is 1. Oh, God. That, I must say, that problem set was kind of a nightmare. If you can do all of this, you should have 0 difficulty with the actual assignments. Okay. Looking at it now, and I'm thinking, wow, look at this. But it's excellent practice. All right, I'm going to say this one more time. I hope it cooperates with me, and then I'll be posting this along with the video. And don't forget, this one had to be broken up into 2 parts because of the electricity thing. So you'll see it in Blackboard and on my YouTube account as Chapter 3 problem set solutions, something like that, parts 1 and 2. Okay. So anyway, the next lecture will be Chapter 4, where we dive very deeply into integrals or antiderivatives, and we'll see that there's a lot of important rules that we'll learn as we go along. But first, we have to take a step back and explain exactly what an antiderivative is. And we'll see that really what it is, it's an area under a curve. Okay, what we're essentially creating is a sequence of rectangles under a curve. And the sum of those rectangles is what we mean by our integral or antiderivative. So it's a little theoretical, but it's important to understand what you're actually doing here. Okay. So anyway, so we'll knock it off here, and next time we meet, it'll be all about antiderivatives. Okay, see you then.